All right, in this lesson, we're going to be talking about the Lagrange error bound. All right, so when a Taylor polynomial is used to approximate a function, we need a way to see how accurately the polynomial approximates the function. How much the approximation is off by is referred to as the remainder or the error of the Taylor polynomial. In general, the function equals polynomial approximation plus the remainder. All right, so we have our function. We have our Taylor-Maclaurin polynomial, which is our approximation of our function, and we have our remainder. All right, for example, if this was our function and this was our Taylor polynomial approximation, then at some point, all right, so let's say here's some point A, then we've got our function, which is this guy in blue. We've got our polynomial approximation here, and then our remainder is going to be that distance right there. All right, that's our remainder. We're going to call it a capital R. All right, but we're kind of going to use the words remainder and error interchangeably in this section. Oops. That section right there. All right. Okay, so likewise, we can solve for the remainder and say the remainder equals our function minus the polynomial approximation. Okay, so let's see, our polynomial approximation, that's our P sub n. So again, we've got our symbolic versions here. Same equations, just written symbolically instead of in words. Again, that first one goes with the first equation, second one goes with the second. All right, to find the maximum amount of error, we will use the first discarded term of the approximation, much like we did when finding the error of an alternating series. There are two typical forms for this in AP Calculus. They essentially mean the same thing, they're just expressed a little differently. So the big idea for this section is barely different than what you've already done with finding the error in a Taylor-Maclaurin polynomial for a alternating series or for the sine, cosine, and exponentials or and natural logs that you've already done. All right, it's looking at that next term after the partial sum that you're using as your approximation, as your error. All right, so let's look at this. So Taylor's inequality. If the absolute value of, and be careful about notation here, f to the n plus 1th derivative, right, notice that's in parentheses, of x is less than or equal to capital M. This capital M here, this is just our maximum value that our error is going to be. Then the remainder of the Taylor series satisfies the inequality remainder equals absolute value of our function minus our polynomial approximation is less than or equal to that max value m over n plus 1 factorial times absolute value of x minus c to the n plus 1 power. All right, again, you'll notice that should look pretty familiar, especially the right side of that inequality, as just a term in the polynomial approximation series. All right, Lagrange error bound, or the Lagrange remainder, says if a function f is differentiable through order n plus 1 in an interval containing c, which is the center still, then for each x in the interval there exists a number z between x and c such that f of x equals, and then you've got your Taylor polynomial there at the end, and then plus that remainder, where the remainder is given by r sub n of x is less than or equal to absolute value of f to the n plus 1th derivative of z over n plus 1 factorial times x minus c to the n plus 1 power. All right, we call that the Lagrange error bound. Ooh, that's a lot. That's a lot of symbolic notation there. So let's see what this means, because these first couple examples, hopefully we'll kind of draw out that we're not doing a whole lot new here. We're just being a little more specific about what this error means and how we can use it in different problems. So the key underneath those boxes, the key is to maximize the absolute value of the n plus 1th derivative of f at z, or we can call that m, that maximum value, and the x minus c to the n plus 1th power pieces over the given interval. Sometimes you will be given that or m, sometimes you will be given an interval. If you're given neither, assume that the interval is from the center to the x value you are using in your approximation. All right, let's look at the first example. All right, again, I think these examples, as you work them through, and feel free to pause and try them on your own first if you like, then hopefully you'll see that we're doing things really similar to what we've already done in this unit. We're just kind of pulling it all together in this last topic here. All right, example 1 says, let f be a function with 5 derivatives on the interval, closed interval from 2 to 3. Assume that the 5th derivative of f of x is less than or equal to 0.2 for all x in that same interval, and that a 4th degree Taylor polynomial for f at center is 2 is used to estimate f of 3. All right, so part A says, how accurate is the approximation? Give 3 decimals. So if we're looking for accuracy, then we're looking for that error. Okay, we want to see what's the biggest our error could be. That's going to tell us how accurate we are. So our error comes from absolute value. In this case, that 5th derivative of our function at x. All right, and since we are looking at that 5th derivative, then we're going to be dividing by 5 factorial times that x minus 2 to the 5th power. All right, thinking about that term in our sequence, and we can pull that straight from those boxes we were just at. If we're looking at our either one, this guy here or this guy here, they both represent that remainder, that error. Okay, so let's see what we can get from this. Okay, so we're told that our 5th derivative of f of x is less than or equal to 0.2. So that's the biggest it can be, is that 0.2. That's our max. That's what we're going to use for that term there. All right, 5 factorial is 120. And for the x minus 2, we're asked to estimate f of 3. So let's go ahead and plug that 3 in. We're going to get 3 minus 2 to the 5th power. Well, 3 minus 2 is just 1. 1 to the 5th power is just 1. So we've got 0.2, which is 1/5, times 1 over 120. That's going to give us that 1 over 5 times 120 is 600. So our error is less than or equal to that value there. Again, we used what that maximum value, that m value there, to show that our error's got to be less than that or equal to. So it says in part A, give 3 decimal places. So we can say our error is less than or equal to, and 1 over 600 rounded to 3 decimal places is 0.002. All right, part B. Suppose that p sub 4 of 3 equals 1.763. Use your answer in part A to find the interval in which f of 3 must reside. Okay, so f of 3 is going to be between 2 values. It's going to be between let's see, looking at our function is going to be between our approximation plus or minus our error. So if we have our f of 3, then it's going to be greater than or equal to the polynomial approximation, which is this guy right here, 1.763, minus whatever our error is, and it says use that from our answer in part A, so 0.002. And it's got to be less than or equal to our approximation, 1.763, plus whatever our error was. Okay, again, we're just saying that the actual, that f of 3, our function, is going to be within that error plus or minus of our approximation that we found, all right, or that we're given in this case. All right, so just to simplify, on the left side of that inequality, that's going to become 1.761. And the right side is 1.765. All right, part C says, could f of 3 equal 1.778? Why or why not? And also, could it equal 1.764? Why or why not? Okay, so let's start with the first one, 1.778. Well, let's look at our interval here. Is 1.778 within that interval? No, it's going to be over here to the right of that upper bound. So, no. That number is outside the interval. Oops. The error would be too large. All right, how about the second one there? All right, 1.764. Okay, that is within that interval. All right, on the upper side of that interval. So, yes, so that fits within that inequality. So for that second one, yes. The value is inside the interval. And the error would be less than 0.002. Okay, let's look at example 2. All right, it says the function f has derivatives of all orders for all real numbers x. Assume that f of 2 equals 6, f prime of 2 equals 4, f double prime of 2 equals negative 7, and the third derivative of f of 2 equals 8. All right, so interesting. They don't give us our function, but they evaluate it for x equals 2 for the original and for the first 3 derivatives there. All right, part A says write the third degree Taylor polynomial for f about x equals 2 and use it to approximate f of 2.3. All right, so it says third degree Taylor polynomial. So let's write our third degree Taylor polynomial. All right, to do that, and it says about x equals 2, so our center is 2. So we need our function evaluated at 2 first, and then our first derivative divided by 1 factorial times x minus c, or to the first power, plus our second derivative. We'll come in and plug in values into this after we write out our polynomial. All right, again, we're just kind of following that pattern for our Taylor polynomial. And it says, what does it say? Third degree, so one more. So third derivative of our function at 2 over 3 factorial times x minus c to the third power. All right, so now let's plug in. Let's see what we get. All right, this is our p sub 3. All right, so f of 2, we're pulling from what they give us here. All right, so f of 2, they tell us it's 6. F prime of 2, they tell us it's 4. We don't need the 1 factorial. The c value, our center, is 2. So we can go ahead and plug that in. F prime of 2 is negative 7. 2 factorial is just 2, so that's going to be minus 7 over 2. X minus 2 squared plus our third derivative of 2 is of f at 2 is 8. 8 over 3 factorial. 3 factorial is 3 times 2, which is 6. So let's see, 8 over 6 is just going to be 4 thirds. So it's going to be 8 times x minus, 2 cubed. All right, so there is our third degree Taylor polynomial. All right, so that's done. So then it says use it to approximate f of 2.3. All right, so f of 2.3 is going to be approximated by our polynomial that we just found, our third degree, at 2.3. All right, so if we went in and we plugged in that 2.3 for each of those x's, those differences are going to just be 0.3. For time's sake, plugging that into our calculator, we're going to get 6.921. All right, that would be our approximation of our function at x equals 2.3. Great. Part B says the fourth derivative of f satisfies the inequality absolute value of fourth derivative of f of x is less than or equal to 9 for all x in the enclosed interval from 2 to 2.3. Use the Lagrange error bound on the approximation f of 2.3 found in part A to find an interval from a to b such that a less than or equal to f of 2.3 less than or equal to b. Okay, so looking for our error here. All right, so absolute value of our error is going to be less than or equal to that. That absolute value of that fourth derivative over 4 factorial times x minus 2 to the fourth. All right, that would be that next term again in this partial sum of the thinking about the infinite series. This would be the partial sum going out to the third degree. That next term, if we were to find the fourth degree Taylor polynomial, all right, this would be that next term, which again is going to be that that maximum error, that maximum remainder. All right, so what do we got here? We've got that it is less than or equal to 9. Okay, so let's substitute that in for our m value. All right, 9 over 4 factorial, which is 24. And then x minus 2, well, our x value is 2.3. So 2.3 minus 2 to the fourth power. All right, putting that into our calculator, we get that our error is less than or equal to the 0.003. Okay, so what do they ask us for? They said use that error bound to find an interval that has f of 2.3 in the middle. Okay, so if that is our remainder, our error right there, let's take what we got for our approximate in that last problem, and let's add it and let's subtract it to that, put it on either side of our actual f of 2.3. So actual has got to be greater than or equal to this 6.921 minus that error, which is 6.918. And it's got to be less than or equal to that approximation plus that error. Okay, so 6.924. All right, so there's our A, there's our B. We know our actual is within that interval there. Okay, part C, based on the information above, could f of 2.3 equal 6.992? Explain why or why not. All right, so 6.992, is that within that interval? No, 6.992 is going to be above that. Again, like in example number 1. So no. Greater, it's a E. Greater than 0.003. All right, the error would have to be greater than 0.003. That one's too big. All right, so again, using that Lagrange error bound, using either of these two representations to show the remainder and how it relates to the actual function value and the polynomial approximation. We'll look at some more examples in our next video.